Uh, Good evening, everyone. Welcome to the ninth session of mine for the course Design of Reinforced Concrete Structure offered by NPTEL. I am Harshit Agrawal, a PMRF research scholar from IIT Bombay, and I will be conducting weekly live session for all the 12 weeks of this course. So just to start with, what is this session all about? So these are doubt clearing and interactive session. They will be conducted weekly every Tuesday from 6 p.m. to 8 p.m. till the course runs. And how we interact in this class by answering to the questions that I'm asking in the chat box, by posting your questions in the chat box, or by raising hand, unmute, and asking your queries. Apart from the class, you can always use the discussion forum of the course where you can post your queries, the answer to which will be addressed there only or either in the next live session by any one of the teaching assistants. And these live sessions will help you to answer the graded assignments easily and will help you to further understand the complex topics holistically. So, in today's live session, we will first have a look of at what we discussed in the last live session that was for week 8 of the course. Just a quick glance. Then we'll discuss the content, week 9 content, wherein first we'll solve one remaining numerical on design of slender column, and then we will start a discussion on design of RC footings. So in this, we will first go through the basics like need, engineering domain, and types of footing. Then more specifically, we will look at different design parameters related to the footing, starting from dimension, depth, reinforcement, and development length. And finally, we'll look at a design numerical on for RC footing, and we'll see reinforcement detailing in that. So let's and finally we will conclude the session. Okay. So in the last live session of mine, we talked about design of reinforced concrete columns, wherein we first understood the practical application of different support conditions. Like there are hinge support, roller support, fixed support, and when we talk about effective length, why we are talking about effective length, where this practically come into action, so that we discussed first. Then we moved into discussion about eccentrically loaded columns. So a week before that, in week 7, we started our discussion on column, in which we discussed about axial loaded column. Now we are talking about eccentrically loaded column. So in that, we first did a numerical on uniaxial loaded short column, and then we saw biaxial loaded short column and a numerical on it. And finally, we started our discussion on the fundamentals behind slender column design, and how that additional moment due to slenderness comes into play. Okay, so I hope everyone is clear with the discussion from the last live session. So just to brief the last part, about design of slender column. What are slender column? So technically, if I can define, when the ratio of effective length of the column to the lateral dimension is greater than or equal to 12. So as per IS 456, we say the columns are slender column. Okay, why this 12 is the ratio? Because when the length of the column is comparatively high, what happens? The bending that is happening in the column generates an additional movement due to the axial load itself, and that additional moment is also needed to be taken into account, which is why we term them as slender column. So when there is short column, what will happen? The bending that is there due to axial load will be very small. This bending due to axial load will be very small, is very small or easy, practically zero. So there is no additional movement that is happening due to internal eccentricity. But when there is a long column or slender column, what happens? The bending that is happening due to axial load leads to such a eccentricity which can itself generate an additional moment in itself. Okay, so even if your load is centrally located, some moment can come due to that load also. So that's why we need to separately study a slender column design. Okay, now in slender column we can have two types of condition: axially loaded slender column, in which the moment will be due to just internal eccentricity, and there can be eccentrically loaded slender column. So there the load is not at the center. So we have moment generated due to both external eccentricity and internal eccentricity. So you need to take care about both the things. Okay. And how this additional moment due to eccentricity is calculated. So as per clause 39.7.1, the additional moment due to axial load in a slender column can be obtained by these equations. Okay. So along both the lateral dimension, I can calculate the additional moment. If I know the axial load which is acting, I know the dimension of the column and I know the effective length along that direction. Okay, so these are the formulas that we use to calculate the additional moment. Okay, now based on this we'll see one numerical first. Okay, so what this numerical says: design a braced column 300 mm cross 400 mm in size, subjected to following conditions. Effective length along both x and y is given as 6 meter. Factored axial load PU is given as 1000 kilonewton. Movement along x-axis at top and bottom of the column is 40 kilonewton and 30 kilonewton. So these are external moments. Okay, and along y-axis it is 30 kilonewton at top and 25 kilonewton at the bottom. And we need to use 20 M20 grade concrete and Fe415 grade steel. Okay, so I will just wait for a couple of minutes. Just try to recap how the design is done, how with external moment we define that point 0.4 m1 plus zero point 0.6 m2, and how we actually take external moment into account. Just think about what we have discussed in the NPTEL classes also, and the session live session that we have covered last week, and then we'll see the solution after a couple of minutes. They must also incorporate SP16, I guess. Like, I haven't explored the software programs that are used to design column, but like in IS 456 itself, there is mentioned that when you need to consider both load and moment and interaction of that, you need to refer SP16. So if the IS 456 itself is saying, then the softwares also might be considering it. I am not sure how it is done in softwares. Or since those graphs must be generated by some logic only, it is not like all practically related, then there should be some numerical formulation behind interaction of load and moment that they might be considering, using which ISP16 was built. Both can be the reason. I will like check if I am able to find how softwares operate, and I will let you know in the next class. Okay, so let's see the solution now. Okay, so first we will write the given data. Like, though it is there in the screen also, but it is a good practice to always write the given data first again. So size of the column that is known to us, it is 300 mm cross 400 mm. Okay, and effective length right now in this question is given to us, but if it is not given, we know how to calculate, either directly referring to the table 28 or 27 of IS 456, or by calculating the stiffness of the beams and the columns above and below, and then calculating beta 1 and beta 2, and then referring to IS 456. So that is also how we calculate effective length. That part was covered in the NPTEL video, so that I skipped. I have directly moved on to the part where effective length is given to us. Okay, so it is given to us as 6 meters, which is nothing but 6000 mm. Okay, factored load is given to us 1000 kilonewton, and MUX at top is 40 kilonewton, and at bottom is 30 kilonewton. MUY at top is 30 kilonewton, and at bottom is 25 kilonewton. Okay, so since there is some external moment also in this question, this is this criteria. This uh, belongs to this uh, condition. Eccentrically loaded slender column. So we have some moment external due to design load also, and there will be some moment due to eccentricity also. Okay, so this is what it is given to us now. Just moving forward. Okay, so first we need to check. So step one will be check for slender column. Okay, though we know it will be a slender column only, but it is always a good practice to check once. So LEX upon D will be 6000 divided by 400. Okay, so it is coming out to be 15, which is greater than 12. And LEY upon B is 6000 upon 300, which is 20, again greater than 12. So therefore we can say the column is long, slender column in both direction. Okay, now what is the step 2 to calculate the moment, net moment? So my net moment will be nothing but m external plus m due to eccentricity. Okay, but in external also there are two kinds of moment that can come. There is external eccentricity moment or the bending moment that is given. Okay, we need to choose the greater one. Okay, now so how we calculate that? So we have two criterias for judging external moment that is given. Okay, how we judge? We take minimum of zero point 0.6 m1 minus zero point 0.4 m2 or zero point 0.4 m2. Okay, this is m1, this is m2. Okay, so these are the two criteria that we saw in the NPTEL discussion also. Okay, so either of these value we need to take the net effect of the external moment. So what are these external? These are the external moment. One is acting at the top and one is acting at the bottom. Okay, so we need to take the net effect of this moment. How we take? using these two equations. Okay, so minimum of this we consider as the net moment acting along a particular direction. Okay, we'll see later on how eccentricity is also taken into account. So first let's calculate this. So MUX, if I will say, it will be zero point 0.6 times 40 minus zero point 0.4 times 30, minimum of this, or zero point 0.4 times 40. Okay, so what will be the value? So minimum of 12 or 16. So it will be 12 kilonewton meter. Okay, and MUY will be minimum of zero point 0.6 times 30 minus zero point 0.4 times 25, comma zero point 0.4 times 30. Okay, so this will be minimum of 8 comma 12. So it will come out to be 8 kilonewton meter. So we know what is the net moment that is acting due to the external moment that is given to us. Now the next step is to take eccentricity, external eccentricity into account. So how to do that? So we first need to calculate what is the eccentricity, external eccentricity. So Ex will be so eccentricity along x direction, it is given by L upon 500 plus D upon 30, and that should be greater than or equal to 20. Okay, when we are talking about slender column. Okay, so this value will come out to be, we can say, maximum of, just to simplify. Okay, we can write like this also. So eccentricity is nothing but maximum of these two values. Okay, so it will be along x direction, this will come out to be maximum of 6000 divided by 500 plus 400 divided by 30, or 20. Okay, so this will be maximum of 25.33 comma 20. So we will have 25.33 as my eccentricity along x direction, and along y direction it will be maximum of L by 500 plus B by 30 comma 20 mm. So this will be nothing but maximum of 6000 by 500 plus 300 by 30 comma 20. So maximum of 22 comma 20. So this will be 22 mm. Now due to this eccentricity, what load will have? So therefore what moment will come? So mu due to this external eccentricity will be given nothing by uh, the axial load times the eccentricity Ex. So this will be 1000 times 25.33 into 0.001, just to convert millimeter into meter. So this value will come out to be 25.33 kilonewton meter. Okay, and mu due to external eccentricity along y direction will be given by design load into eccentricity along y direction, which is 1000 into 22 into 0.001. So it will be 22 kilonewton meter. Now compare these values with these values. Okay, since this value is more than 12 kilonewton meter and this value is more than 8 kilonewton meter, so we can write the external moment that is needed to be considered will be 25.33 kilonewton meter along x direction, and MUY will be 22 kilonewton meter along y direction. I hope this part is clear to everyone how we came up to this. So externally there are two kinds of movement that are generated, either due to load or either due to the eccentricity due to the load which is acting, or either due to the moment that is acting externally also. Okay, so we need to take maximum of those moment as an external moment in our case. Okay, so we calculated moment due to the net moment due to the external moment which was acting, and we calculated moment due to external eccentricity. And since we found the moment due to external eccentricity is more than the moment due to net external moment, so we took the moment due to eccentricity as our net moment. Okay, now the second, so we have calculated this part. Okay, moment due to design load or external load or external moment, net moment due to external moment. Now we need to calculate the additional moment generated due to internal eccentricity. So how we do that? Using this formula which is given to us. Okay, so using this formula we will calculate the additional moment. Okay, so I will take a new slide. Okay, so my step 3 is the calculation of additional moment. Okay, I will just cut this part and bring it up. So additional moment along x direction, it is given by pu times b upon 2000 into L effective along x direction into dimension along x direction per square. Okay, so if I will substitute the value, it is 1000 times b is zero point 0.4 divided by 2000 into 6 divided by zero point 0.4 square. Okay, so upon doing the calculation, you will get a value of 45 kilonewton meter. So this is additional moment along x direction. Now what is additional moment along y direction? So similarly, we can calculate along y direction also. Just we need to change d by b. Okay, so this is the formula L effective along y direction upon b square. So I have the values 1000 into zero point 0.3 divided by 2000, 6 divided by zero point 0.3. Okay, square. Okay, so upon doing this calculation, you will get a value of 82 kilonewton meter. Okay, so these are our additional moments that are generated due to slenderness. Now, once we know the additional moment due to slenderness and the external moment that is acting, we can calculate total design moment. So my step 4 is calculating total design moment. Okay, so total design moment will be given by MUX is nothing but MUX external that we calculated. So I will say it as MUX dash. I will put a dash here so that you can distinguish between both, and MAX. Okay, so we know both the values. It is 25.33 plus 45. So it will come out to be 70.33 kilonewton meter. And MUY will be nothing but MUY dash, that is due to external, and MAY due to internal eccentricity. So it is nothing but 22 plus 82. Okay, just let me check this calculation once. Is it 82 or something else? Okay, so this is 60, not 82. The 82 is the net moment. Okay, so this value will come out to be 60. Okay, so plus 60, so it will be 82 kilonewton meter. So this is the moment for which we need to design. Okay, we have calculated our design moment. Okay, now we'll move on to the design part. Now we are clear with what is the moment and what is the load acting. So now we need to see the design part. Okay, so let's assume, since we need to choose a particular graph from HP16 for continuing the design, we need to have that assumption whether we are providing reinforcement along all four sides or along two opposite sides only. Because that in that way only we can choose a particular graph for design. Okay, so assume reinforcement is distributed along all four sides. Okay, and I'm assuming a clear cover of what minimum we need, 40 mm. Okay, so 40 mm I am assuming clear cover, and I am taking diameter of reinforcement as 20 mm. Okay, so for these criteria, what will be my effective depth? Because that is also we need when we are choosing a particular chart from SP16. So it is clear cover plus dia by 2. So it will come out to be 40 plus 10. It is equal to 50 mm. Okay. Now let's assume. Okay. So we know d dash by d. So d dash by d. Now we can say. Okay. No, it will be different along both the direction. Okay. Just wait a second. Hmm. So now what we need to do, this is now simplified into our biaxial loaded case. So in that what we did, we know the moment that is acting. Now we need to calculate the ultimate moment along x and y direction, and then using the formula mu upon mu1 square plus m की power alpha plus mu y and mu y dash to the power alpha should be less than or equal to 1. So we need to choose a particular percentage of steel that we need to provide which will fulfill that condition. Okay, remember the numerical that we did in the last class. So for biaxial loaded column, how we design, the same design procedure we need to opt now. Okay, so for that, let's assume generally what percentage of steel we need to provide, between 2 to 8%. So let's assume I am providing percentage of steel as 3%. Okay, so this is what I am assuming for design. So along x direction we will calculate the mu1 mu first, and then along y direction we will calculate. Okay, so this is my assumption. I can remove this part also now. Okay, so along x direction first. So what I have, d dash by d is equal to 50 divided by 400, which is equal to 0.125. I will just round it up to nearest multiple of 5. So I will take 0.15. Okay. And P by FCK also I need. So it is 3 by 20. So it is 0.15. And I know PU by FCK BD also. So PU by FCK BD is nothing but 1000 into 1000. So to convert kilonewton into Newton, divided by 20 into 300 into 400. So this value will come out to be 0.42. So we know the endpoints in our case. Now we'll refer to SP16. Okay, so which chart we need to refer to, in which my d dash by d is 0.15, my p by fck and my grade of steel is Fe415, and reinforcement is equally distributed. Okay, so we'll just check which graph is that one. Okay, so Fe415 first. Okay, we are at Fe415 and d dash by d is 0.15. Okay, reinforcement distributed equally along on two sides. So this is not the case. We need distributed along all four sides. So distributed along all four sides. This is Fe 250, and now we need Fe 415, right? Yeah. So it is chart 45. Okay, so reinforcement distributed and equally along all four sides, Fe415 and d dash by d is 0.15. Okay, so if I see in this chart, so which point I need to choose? My PU by FCKBD, it came out to be 0.42, so just near somewhere here. And my P by FCK value is 0.15. Okay, so you can see here 0.15 will lie somewhere in between this, and 0.42 is this. So you need to track here till this stage and you need to come down. Okay, so this value will be close to just above this point, above the mid mark, just near this. Okay, okay, so I have done the calculation previously also, so just I will use that for now. So what chart we are using? Using chart 45 of SP16, we get what value we are getting of mu by FCK BD square. So this we say as mu x1. So mu x1 upon FCK BD square will get around 0.16. 0.16 to 0.17 will get. So I am taking the midpoint 0.16 side. So from this I can calculate mu x1. So it will be 0.165 times 20 times 300 times 400 times 400. Okay, so this value will come out to be 158.4 kilonewton meter. Similarly, along y direction also. So along y direction, we have d dash by b as 50 by 300. So it is nothing but 0.16. We will round up it to nearest value. So 0.15 we will take. P by FCK is the same, 0.15, and PU by FCK square is also the same. PU by FCK is also the same, it is 0.42. Okay, so we need to refer to the same chart only, I guess. Okay, since D dash by D is the same, P by FCK is the same, and PU by FCK is the same. So again, using chart 45 of SP16, we get, so we'll get the same value. Since all the values are the same, this value again will be the same. Okay, so mu y1 will be the same as mu x1 only. So I can just rewrite that part. So mu y1 and mu x1 both will be the same for us. Okay, just one change in calculation will happen. Instead of bd square, it will be db square. Okay, so here we need to change that. Okay, since our b and d are changing, so it will be db square. So this value now will change to 118.4 kilonewton meter. Okay. So now we know mu x1 and mu y1. We know mu x and mu y. Okay. So and we need to calculate alpha, that power coefficient. Okay. So from clause 39.6 of IS 0.456, we can say PUZ is equal to 0.45 FCK AC plus 0.75 FY ASC. Okay, so what will it will come out to be 0.45 FCK is 20, AC is nothing but AG minus AC. Na? So AG I know gross area, it is BD, and 3% steel I have provided. So my ASC will be nothing but 0.997 times AG. So 0.97 times 300 times 400 plus 0.75 times 415 times 0.03 times 300 cross 400. Okay, we provided 3% steel, so I am multiplying 3% there and 97% here. Okay, so upon doing the calculation, you will get UZ as 2168.1 kilonewton, and you know the PU. So PU upon PUZ ratio will come out to be 1000 divided by 2168.1, so it will nothing but 0.46. Okay, so we know for point 2 ratio alpha n value is 1. For point 8 ratio alpha n value is 2. So by interpolation we can calculate what is the alpha n value. Okay, just simple interpolation if you will do, you will get the value. So I'm just writing directly, just I'm not showing that mathematical part. So your alpha n will come out to be 1.42. Okay, now for 3% steel to be safe, what we need, okay, I have assumed this, okay. Now I need to check whether this was safe or not. So for this to be safe, as per IS 456, MUX upon MUX1 that we calculated to the power alpha n plus MUY upon MUY1 to the power alpha n should be less than or equal to 1. If this is coming out to be true, then we say our design is true. So just substituting the value 70.33 upon 158.4 to the power 1.42 plus 82 divided by 118.8 to the power 1.42. Okay, so what this will come out to be 0.44 to the power 1.42 plus 0.69 to the power 1.42. So this value will come out to be 0.902, which is less than 1. Since this condition is true, we will say our design is safe. Thus, 3% steel is enough. Okay. Now, if we know 3% steel is enough, we can calculate number of rebars. So number of rebars will be nothing but area of one steel rebar upon total area of reinforcement. So total area of reinforcement, what it is, 0.3% of BD. So 0.03 into 300 into 400, it will come out to be 3600 millimeter square. So N will be nothing but 20 pi r square, 0.25 pi d square upon total area of reinforcement, which is 3600. So this value will come out to be 12 numbers. Okay, if you will round up. So you need to provide 12 number of rebars all across the section for safe design of a slender column. And the design of transfer reinforcement, I don't think we need to show. So last part is design of transfers reinforcement. So that thing is clear to everyone. Okay, what are the two criteria? Diameter is one criteria, and spacing is one criteria. So I will directly write the answer for that. We need to provide 6 mm diameter tie bars at the rate 300 mm center to center. Okay, you can cross check with the conditions that are required and you can verify. Okay. So this is how we design. So you need to provide 12 numbers of rebar equally along all the sides. So how it will be done? So I will just show you a very rough diagram. Okay, suppose this is my cross section. Okay, so I will have one rebar at here at corners. Okay, and I need to provide eight more. So two here in between. Okay, so this will be my top view and side view, something like this. So this will be my tie bars. These are my longitudinal bars which are running, and this will be my tie bars. So these tie bars are a 6 mm in diameter, and the spacing is 300 mm. Okay, so this is how we design a slender column. I hope you are clear with the discussion. Any doubt in the design? Okay, so if there are no doubts, we will proceed ahead. So now we will talk about reinforced concrete footing. Okay, so generally, basically, what are footings? So footings are those structural elements which are present, which exist below the ground level. So you can see in the images also. So these are footings. Okay, they are present below the ground level. So this is a singular footing. This is combined footing. This is leveled footing. Different dimension footing. Okay, so how when we initially talked about basics of reinforced concrete structure, we saw how load transfer is done. So from slabs it comes to beams, then columns, and finally it comes to footing. So if we see, it is a floor. From slab it comes to underneath beams, okay, then to columns, and then from column finally to the footing. Okay, so what is the role of this footing in the structure? So if we see from this point, so ultimate load of any structure is supported by the underlying soil. Okay, but since soil is much weaker compared to steel and concrete, we need a higher area or volume of soil to carry a given load. Okay, so steel and concrete are generally very strong. Okay, but soil is not that strong. So you can't just see like column you're embedding in soil, and you're expecting that the soil will take up the pressure created due to the load acting on the column. You need a higher area which can take up this load. So for that we need to provide a footing which act as a load transfer element from structure to underlying soil. So footings are these high surface area members which connect the load from the structure and transfer it to the soil. Okay, without failure of soil or failure of structure. Is there some doubt? Okay. Okay, so I hope the load transfer mechanism is clear. What is the role of footing and why we are providing footing? Just to support the soil such that it can carry the load. Okay, now since footing is an interacting element between the substructure capacity and understructure capacity, there are two fundamental engineering domains that are involved in this design. What are those two domains? Geotechnical engineering and structural engineering. So what geotechnical engineering deals with, they deal with the location and the depth criteria. They see how what is the quality of the soil as per the location, how much bearing capacity that soil can carry without failure, and what amount of settlement will happen if there is some extensive load which is acting. Okay, so these are the things they deal with, the properties of soil, what is the behavior of soil, and what is the safe bearing capacity of the soil. So this bearing capacity is very important for us when we are designing a structure. We need to know how much load a soil can bear. Accordingly we need to provide the dimension of our footing. Okay, we'll see later on how it comes into play. So just remember, from geotechnical engineering we get the bearing capacity of the soil, varying with depth or at a particular region. And a structural engineering, what it does, structural drawing, it provides a structural drawing following the location and the depth criteria, and helps us to design footing such that soil pressure doesn't exceed the allowable limit. So if we know the bearing capacity of the soil, we need to design our footing such that the pressure on the soil is not exceeding the allowable limit, the allowable bearing capacity limit, and such that structure is also safe against any settlement. Okay, so this is how two fundamental engineering domains are interacting for designing a footing. So our focus is not on the structural engineering part. So we will take this bearing capacity directly. We will assume this bearing capacity directly, and then we will focus on the design part. Okay. Now, based on the location, properties of soil underneath, and the size of footing or spacing between them, there are two types of footing. One is shallow footing, footing or foundation, both we can say. A combination of footing is known as a foundation. So we can say as foundation or footing both. So there is shallow foundation and there are deep foundation. When we say it is a deep foundation, when the depth of the footing, the ultimate depth of the footing is greater than the dimension of the footing, then we say it is a deep foundation. And if it is less than or equal to the dimension of the footing, we say it as a shallow foundation. Okay, this is just a basic part that I have picked from geotechnical engineering domain. So you don't need to think much about this when you are a structural engineer, just so that you know what is shallow and what is deep. I introduced it here. Okay. Now there can be different types of footing based on the dimension. So first is isolated footing. So these are the footings. Suppose this is my top plan view. Okay. So these are the footings that lie like this. Okay. So underneath different column we have different footing. So such footings are known as isolated footing. We are designing each of them separately. Now second type is isolated footing plus with straps. So sometimes what happens between footings, we need to also provide some straps so that it can bear all the loads. Okay. So this type is known as isolated footing with straps. So strap is nothing but a conducting element between two isolated footings. Okay. Now third type can be, suppose the spacing between these two footing is not much, less than 10 mm or say 20 mm, due to the dimension. This is very large dimension footing and this is also very large dimension footing, and the spacing is not much between them. So what we do, we provide a combined footing for both. So it is like this, combined of both the footing. Okay, so in some cases this is also that we can provide. Okay, we saw in the example also. Okay, so see this was a combined footing, this was an isolated footing. Okay, then there can be mat foundation. Suppose my footing across whole uh, foundation part is very large, like these are my footing, there is no gap between footing much. Okay, so what we do, we provide a single footing beneath the structure, which is known as mat footing. Okay, and finally we have pile footings. So what happens, suppose this is my ground level. Okay, and my soil properties varying with the depth. Suppose uh, the top layer of the soil is very weak, it can't take load. So what we need to go, we need to dig very deep inside the soil so that it can take the load of the structure, and in the such cases we provide pile footings. Okay, so these are generally circular or thin column like only, and that go very deep inside till even the stone level also it can go to support the load of the structure. And these are generally provided when we talk about bridges. So in bridges, when there is water underneath, we need to go a lot deep inside the soil also so that it can bear the load of the above structure. And in such cases, we design for pile footings. Okay, so in today's class, our focus will be on this isolated footing design. Okay, because this combined footing, mat footing, everything is just a like different types of footing that we are talking about. We need to understand how a footing is designed, how design is done. So for that we'll focus on isolated footing. Okay, so what are different design parameters that are related to design of footing? So first is the area of footing. Okay, so the area of footing that is provided depends upon two main properties: the ultimate load that is coming from the substructure and the safe bearing capacity of the soil. Okay, now how this ultimate load is calculated? So as per IS 456, these are the three load combinations that we need to take when we are designing for ultimate load. So we don't take any factor of safety into account. We just take load combinations like this. If we are given dead load and imposed load, both like this, if wind load or earthquake load is given like this, and if both the imposed load and wind load or earthquake load is coming like this. Okay, so based on this we calculate the service load acting on the footing, and we know the safe bearing capacity of the soil beneath. Okay, so this is something in kilonewton or Newton load, and this is something in Newton per millimeter square. Okay, so dividing the service load by the safe bearing capacity of the soil will get the area of footing that is necessary to be provided so that there is no soil failure. Okay, so first step is to decide the area of footing. Now, once we know the area of footing, we need to check what is the ultimate soil reaction that is coming. Okay, so here we went with service load, like without any factor of safety that we took into account. For ultimate load bearing capacity, we need to take the factored load design. And since we know the area of footing and the moment acting, so there can be both load and moment. Okay, so we need to calculate the ultimate soil reaction. How it is calculated? By this formula. Okay, just reverting this formula, safe bearing will come here and area will come here. So what will happen? My bearing capacity of soil, it will be nothing but factored load upon dimension of footing plus of minus 6 times m by bl square. How this came? This is nothing but m by I, m by y, and which is nothing but I by l. Okay, so using that formula, it came BL square by 6. Okay, so since there is some moment also acting, so this is the eccentricity part which can be created. So that's why there will be a maxima here and minima here. Okay, in the safe bearing capacity, and this distribution is also important for us to know so that we can design for the reinforcement that is actually needed. Okay, so based on this value Q1 and Q2, it is plus minus. There can be three cases. Okay, my both Q1 and Q2 is positive, so my reaction will look like this beneath my footing. So this is my side view of footing. Okay, just don't get confused. Second case can be my Q1 is positive and Q2 is 0. When this can happen? When the smaller part becomes 0. So this will happen when my eccentricity, which is acting at the top, is L by 6. So in this case, what will happen? The one part will be 0 and one part will be maximum. Okay, so this case is when uplifting is at its critical position. And when my Q1 is positive and Q2 is negative, what will happen? My movement diagram, the bearing capacity diagram will look like this, and this part is prone to get lifted up due to load. So this is my structure now. So this part is under compression and this part is under tension kind of thing. So this rotation can happen here. So we need to first check which criteria we are belonging to so that we can provide reinforcement accordingly. So in these cases, we need to provide only tensile reinforcement. But here we also may need to provide the compression reinforcement also because of the opposite moment which can be acting due to the load beneath. Okay, so these are the three criteria based on the moment and load that is acting on the footing. Now, this was the second part where we calculated the ultimate soil reaction. The third part is the most important part is the thickness of the footing. So, as per IS 456, the thickness of the footing shall be sufficient to fulfill three conditions. What are those three conditions? Sufficient to resist shear force without using shearing steel. So, generally, in case of design of footings, we don't provide any shear reinforcement. So we need to provide thickness of footing such that we don't require shear reinforcement. And when it can come, when my design shear force, the shear force that is acting due to the load is less than the shear strength of the concrete. Remember when we talked about beam, if this condition was coming up, we provided minimum reinforcement, minimum shear reinforcement. But in case of footing, we don't provide that minimum reinforcement also. So we need to make our thickness such that this condition is getting fulfilled. Okay, second condition is sufficient to resist bending moment without compression steel. So what it means, we can't provide doubly reinforced section. So our thickness of the section should be such that only tensile reinforcement is enough to carry the moment. There is no requirement of compression reinforcement until there is upward bending also which can occur. Okay, and third is to withstand corrosion that can be caused from the surrounding side. So for this, we need to provide sufficient depth and cover so that our tensile reinforcement is safe against corroding ions present in soil. Okay, so this is generally more from a code point of view that we choose, but for first two, we need to design. We need to check whether our thickness is enough to resist shear also and bending also. Okay. So what are the criteria of minimum reinforcement? So minimum 0.15 or 0.12% of gross area we need to provide as reinforcement when we are taking FE41, FE250 or FE415 steel. And for cover, it should be not less than 40 mm. Okay, if footing is not directly in contact with soil. So if my footing is not directly contacting the soil, if it is covered by sand and sand is covered interacting with soil, in such cases my cover should not be less than 40 mm. But if my footing is directly in contact with soil, my cover should be at least 75 mm. Okay, so you can see, compared to substructures where we used to provide cover of 25 mm or 30 mm or 40 mm, in case of footings we are providing a very high cover so that our reinforcement is safe from any corrosion. Okay, now how we calculate thickness? We know two criteria, okay, that thickness need to satisfy, but how we choose the minimum thickness that we need to provide? So the thickness of the footing that is provided shall satisfy two criteria: bending and shear, that we saw earlier. So in terms of bending, the critical section of failure due to bending is taken as the face of the column. Okay, so there is some moment acting on the column. Okay, so if we draw the side view, what will happen? Something like this bending will occur. So my face of the column is taken as the critical section where failure can occur, and so for at that section we need to check what is the minimum thickness of footing we need to provide. Okay, so how we can check that? We know bending moment, what there is some soil pressure acting below. Okay, so if I assume there is uniform soil pressure acting below, so I can calculate the bending moment acting at this face due to the soil pressure. How it will be given by, suppose this is q, so it will be nothing but q into b into l minus a by 2 ka whole square. So this much is the bending moment acting here. So this part I will equate as 0.138 fck bd square or something, and I can calculate what should be my depth of the section, minimum depth of the section to support this bending. Okay, so this is how we can do the calculation. Okay, so this is first criteria from which we'll get the minimum thickness. Okay, second criteria is shear. So in shear, there are two types of shear when we talk about design of footing. There is one-way shear and there is two-way shear. So when we see, suppose this is my footing, okay, and this is my effective depth. Okay, so generally we assume that shear crack propagate along 45 at a 45 degree. So if this is D, so this will also be equal to D. So my critical section of failure which is happening here is at a distance D from the face of the column. Okay, so that's why we can take critical section of failure in one-way shear at a distance d from the face of the column. So at this distance d from the face of the column, I will calculate the shear force which is acting. So it will be nothing but, since q is my uh, net reaction of soil, so q times b times l minus a by 2 minus d. So this distance I need to calculate. So this distance is nothing but this. So I can calculate net shear acting here. Okay. So this will be my shear force, and my allowable shear is, it is nothing but tau c into L into D. How we'll get tau c from IS 456? We can get based on the grade of steel that we, based on the grade of concrete and percentage of steel reinforcement, we can get tau c. So L into D, when we will equate these two, we'll get the minimum thickness to resist the one way shear. So we got minimum thickness from here bending, and then we got minimum thickness from one way shear, and similarly we'll get a minimum thickness from two way shear also. So we say for punching shear, the critical section of failure lies at d by 2. So in this we calculate the shear force again. It is nothing but we need to subtract the area. Okay, so this total area minus this area enclosed at a distance d by 2. So due to this whole sharing the net reaction of soil acting in this area, we calculate the shear force acting at a distance d by 2 like this, and then we calculate the allowable shear force. So it is given by tau p times the parameter of this area, okay, at a distance d by 2. So it is nothing but d times 4 times a plus d, and tau p is given by 0.425 fck. Okay, so allowable punching shear we can say, that the concrete can resist. So based on this, we will again get a D. So the D that we need to provide should be maximum of these three, so that failure can't happen due to any of these conditions. So minimum thickness that we need to provide should be max such that it is satisfying the bending moment, the one-way shear criteria, and two-way shear criteria. Once this is done, now we have the dimension of the footing, we know the depth of the footing, and we know the area of reinforcement that we need to provide. Okay, since when we know the depth of the footing, we can calculate the area of reinforcement very easily, like how we used to do in the beam design part. Once we know the area of footing, now the last important design parameter is the development length. Okay, so what happens? This is my column above, and this is my footing. Okay, so for load to get transferred from column to footing, there should be a transfer element that is present, and this transfer element are generally the rebars. But it is not like rebar directly can transfer load from column to footing. There is a certain embedded length that should be present inside the footing that can carry the load from the column to footing, and this embedded length of steel in a concrete element to design the transfer force is what is known as development length or anchorage length. Okay, to find the development length of the rebar, what IS 456 says, the bond resistance of the concrete and shell shall be equated to the stress acting on the surface of steel and concrete. Okay, so tau BD we get from IS 456 like this table. We know the diameter, and we need to calculate the development length. This is what we know, the design bond stress, and this also we know. So we get the development length. Okay. So based on this criteria, we get the development length, like minimum length that we need to provide for load transfer to occur. When we'll do the numerical, you will get a more clarity of how this length is coming up. Okay. So I hope everyone are clear with all the six parameters. First parameter was area of footing. Second was ultimate soil reaction, in which we'll check for these three cases. Right now we are dealing with the case one only. Okay. Then the thickness of footing and the minimum reinforcement and the cover criteria. Now, what minimum thickness we need to provide? For this, we need to go for three cases: bending moment, one-way shear, and two-way shear. Checking all the three conditions, we choose our thickness of footing. Once we know the thickness of footing, we know the bending moment which is acting. So we calculate the area of steel that we need to provide, and then we calculate the development length that we need to provide. Okay, now we'll see one numerical on this so that we are able to apply all the six steps properly. Okay, so this is the numerical. We will see: design a RC isolated footing for 400 mm cross 400 mm column size, which carries a the load of 1200 kilonewton on the column. Take ultimate bearing capacity of soil as 200 kilonewton per meter square. Assume M20 grade concrete and Fe415 grade steel. So I will pause for 5 minutes, and I will ask you guys to think how to proceed ahead with this solution, and then I will tell the solution. Okay, so let's see the solution now. Okay, so I given data we will write first. So given data is column size I know 400 cross 400 mm. Uh, carries a load. So PU is given to us at 1200 kilonewton. Ultimate bearing capacity of soil is given. So remember, it is ultimate bearing capacity, not safe bearing capacity. Okay, so it is given to us 200 kilonewton per meter square. M20 grade concrete we need to use, and Fe415 grade steel we need to use. So step one will be my load calculation. Okay, why? So just see. Okay, since it is given to us ultimate bearing capacity, if it would have been given to us as the safe bearing capacity, then we would have taken unfactored load. But since ultimate bearing capacity is given, we need to take factored load into account. Okay, either you can go or you can calculate safe bearing capacity. Okay, safe bearing capacity is nothing but ultimate bearing capacity divided by factor of safety, which is nothing but 1.5. So it will come out to be uh, 200 divided by 1.5, which is nothing but you can write for now like this. Okay, now what is the load that we need to consider? So the load that we consider for design, it is the design load, plus we also need to take self weight of footing and the backfill soil. Why? So if you see in the design, so this is suppose my footing. Okay, and this is my ground level. So there may be some weight of the footing also in this soil portion that is here. Okay, so that is also what we need to take when we are, that also we need to take into account when we are designing. So how we take that? By considering 10% of the design load that is given to us. So I assume 10% of the design load as my weight of footing and backfill. Okay, this is as per IS 456, so it will come out to be 1.10 times 1200. Okay, so kilonewton. Okay, so knowing these two values, what will happen? Okay, if I can directly write 10% of 1200, so it will be nothing but 120. So my total load will be 120 plus 1200, which is equal to 1320 kilonewton. Okay, this is my total load which is acting, unfactored load. Okay, so my step 2 will be to calculate the size of the footing. How we calculate the size of the footing? Can you just mute yourself? Okay, so how we calculate the size of the footing? So we know, suppose I am providing a square footing. So my dimension will be B cross B. Okay, so my area of footing will be nothing but the load acting, which is 1320 kilonewton. I will convert it into Newton, divided by the safe bearing capacity of soil, which is nothing but 200 divided by 1.5. So 1.5 will come here. Okay, so this value upon calculation it will come out to be, okay, since it is also in kilonewton, we need to multiply 1000 here. So this value will come out to be 9.6 meter square. So my B will come out to be roughly 3.1 meter. So final dimension of footing will be 3.1 meter cross 3.1 meter. So we have done the size of the footing we have calculated. Okay, now the next step is to calculate the net upward pressure due to the ultimate load. Okay, so how we do that? Okay, since there is no moment that is acting on the column which is given in the question, so it is a simple calculation for us. Okay, so save bearing, everything I will remove. So step 3 is,
Sir, if it is characteristic load, then we should not there is no need to multiply with 1.5.
when you're when you are calculating the dimension, then we don't need to multiply the factor of safety. But when you are calculating the net upward pressure, then you need the factor of safety also into account. Okay, so this is as per IS 456. When you're choosing the dimensions, you don't need factor of safety. Why? Because we are dealing with safe bearing capacity of soil. Okay, so if ultimate bearing capacity of soil is given, then we need to take factored load. But if safe bearing capacity of soil is given, then we need to take unfactored load while designing the size of the footing. But when we are calculating the net upward pressure, then we need to take ultimate load only. Okay. Okay, so step 3 is, so first I will calculate ultimate load. So my ultimate load will be nothing but 1.5 times the load that I calculated. So it will come out to be 19200 kilonewton. Okay, now what is the soil pressure? So my soil pressure will be nothing but total load upon area of footing. So it is 192,020 divided by area of footing is nothing but 3.1 times 3.1, the size of the footing which is we provided, which will come out to be 9.61. Okay, so the ultimate soil pressure from this calculation will come out to be 199.80 kilonewton per meter square. So for safety, I will assume Q as 200 kilonewton per meter square. So if we see in a diagram, so if this is my front view of the footing, so I'm assuming that the soil pressure is uniformly acting at the base of the footing. Okay, and this value is 200 kilonewton per meter, or I can say zero point 0.2 newton per mm square. So this is my Q. Okay, net upward pressure due to soil. Okay, now this was step 3. So step 4 is calculation of thickness. Okay, calculating minimum thickness of footing. So we know there are three criteria: bending moment criteria, one way shear, and two way shear. Okay, so I will provide you better, I will advise you a better thing how to design for this thing. Design minimum thickness based on one way shear and two way shear only. Don't take bending into account right now. Why? Just leave it. You will get a value of D. Once you get the value of D, calculate the area of reinforcement. You know the bending moment which is acting, you know the depth. So calculate the area of reinforcement that is needed and check that area of reinforcement with minimum reinforcement. If it is fulfilling that criterion, then the depth that you have provided is safe for bending also. So you don't need to do the bending calculation twice. Okay, just do it once and later on check the area of reinforcement with the minimum reinforcement criteria. So that will also serve for the safety of depth only. Okay, so that is what we will opt in this question. I explained you in a different way, but that was theoretical part. In numerically, we need to be a little faster, so we will opt this technique. Okay, so first is one way shear. Okay, so in one way shear, we saw how we calculate shear force. So shear force is nothing but Q times B times what was the formula? Q times B times L minus A by 2 minus D. So minus L minus A by 2 minus D. Okay. Now what is my B? B is 3.1. What is A? A is my size of the column, which is zero point 0.4 meter. Okay, and the Q is known to us. Q is 200 kilonewton, zero point 0.2 Newton per millimeter square. Okay, so we know all these three values. This also will take in millimeter only so that dimensions are clear everywhere. Okay, and so this value will come out to be zero point 0.2 times 3100 times 3100 minus 400 by 2 minus D. So just do the calculation once. Let me do 620. Okay, so this will come out to be 620 times 1350 minus D. Now hold this equation as it is. Now we need to calculate the second part, this part, allowable shear force. So that is nothing but tau c times. So allowable shear force is nothing but tau c times BD. Okay, what is tau c? So we need to refer table 19 of IS 456. So if I can show you that table, so this is table 19 of IS 456. So in this, tau c is depend upon concrete grade also, and area of steel reinforcement that we are providing also. But right now we don't know what is the area of reinforcement we are providing. So let's assume a whole figure value only. So let's take minimum 0.15%, so we are providing. So assume 0.15% area reinforcement we are providing. Okay, and our FCK is, what was the FCK in the question? M20. So FCK is 20 MPa. Okay, so for this M20 and 0.28. Not Let's not take the minimum, we should take a little higher. Suppose I'm taking 0.25% reinforcement. Okay, so my tau c will be 0.25 and M20, so it will be 0.36 Newton per millimeter square. Okay, so suppose I take 0.36, this will be my tau c, and B and D I know, B I know, D I don't know. So B is this and D is unknown to us. Okay, so I know both LHS and RHS now. So upon solving, just equating LHS and RHS, what I will get, the value of D I will get. So when you will solve this, you will get D as 482.19 mm. Okay, so assuming a clear cover of say 75 mm, what I will get, capital D I will get as 482.19 plus 75, 557 mm. So let's round up it to 550 mm. Okay, since we can't provide 557 and 600 will be very larger than 550.7. So let's say my D that I am providing, the total depth, total thickness of footing is 550 mm. Now this is for safety against one-way shear. Now we need to check it with two-way shear also. So how to do that? Okay, so now second is two-way shear, or we say punching shear. Okay, so for this, what was the formula? So shear force is nothing but Q times the total area, which is b square of footing, and the area enclosed by d by 2 distance. So d by 2 on either side will become d, and size of column I know, which is a, so a plus b square. Okay, so this is what I need to calculate. So this b square minus a plus b square. So we know q is zero point 0.2 Newton per millimeter square, p100 square minus a is 400, and d, this is capital D. Okay, and d is 550. So 400 plus 550 is 950 square. So we have assumed that D that we get from first one-way shear. Let's assume that D is sufficient. Suppose that D is sufficient. So if it is sufficient, it should satisfy the two-way shear criteria also. Okay. So this value of shear force will come out to be 1741.5 kilonewton. Now, what is the allowable shear force? So, if my shear force that is coming, if it is less than the allowable shear force, then we can say that the thickness that we are providing, 550, is sufficient. So, my allowable shear force is nothing but tau p times uh, uh, d into A plus D. Here always remember this D is capital D when we are talking about constraints here, okay? So that you are not confused. This is capital D. So my formula is tau p times D times 4 into A plus D. So tau p times D, which is 550, times 4 into A plus D, which is 400 plus 550. And now I can calculate the value of tau p, 0.25 under root fck. So if we'll do 0.25 under root of 20, it will come out to be 1.18. So 1.118 times d, 550, times 4 times 400 plus 550. So what this value will come out to be 2336.62 kilonewton. Since my shear force is less than allowable shear force, I can say I can say total depth of 550 mm is sufficient. Okay, so this is that the depth that we have chosen is safe, sufficient, or you can say safe. Okay, now next step is reinforcement detailing, and reinforcement detailing only will check the minimum reinforcement criteria. Okay, so step 6 is reinforcement detailing. So for that we need to first calculate the ultimate moment which is acting. How we can calculate it? By the first condition. So bending moment is nothing but Q times B times at the face. So Q times B times L minus A by 2 square. QB by 2. Okay. WL square by 8 we write now. So similarly like that. So this substituting the values, it will come out to be zero point 0.2 times 3100 times L minus A. So 3100 minus 400, 2700 square upon 8. So 2 into 4, it will come out to be 8. So this moment will come out to be 564.957 kilonewton meter. Okay. Now what is the expression of mu with AST? So we know from the design of beam part, it is given by 0.87 Fy ASTD 1 minus x by d. So x by d is nothing but AST times Fy upon BD FCK. So BD FCK. There is a direct formula also, but this is the general formula. So you know all the values, you know mu 564.96975. You know Fy, we know D, and we know B also. Okay, so all the values we know. So substituting all the values, we'll get the AST. So upon solving, you will get AST as 2951.4 mm square. Okay, now what is AST minimum? Since this is Fe415 steel, so AST minimum is 0.15 times gross area. So 0.15 into 0.01 times 550 into 3100. So just do the calculation. So it will come out to be 557.5 millimeters square. Since my AST is more than AST minimum, I can say that my depth is sufficient. Okay, so we are safe. So this total depth is safe for all three criterias. Okay, like this we can also do. Once this is done, what we need to do? Step 7 is, no, step 6 only, number of rebars that we need to provide. So let us assume 16 mm diameter bars that we are providing. Okay, now you know the total area of reinforcement, you know the area of one rebar, so you can calculate the number of bars. So I'm just directly writing what will be the results. Number of bars is area of one rebar divided by total reinforcement area. So it will come out to be 14.68 numbers. But since we can't provide such numbers, so we will provide 15 numbers of 16 mm diameter bars. Okay, along both the side. Okay, along x and along y. Okay, since moment can occur along both the side, so we need to provide along x and y direction both. Spacing we can easily calculate. Okay, we know the area of one reinforcement and total reinforcement. We know the value of b. So what will be my spacing? So spacing is nothing but area of one reinforcement upon total AST times b. So it will come out to be around 200, 211. So we are providing 210. So at 210 spacing, we need to provide 15 number of diabars along both the sides. Now my step 7 is the check for development length. Okay, this is the final check. So how this is done? So we saw this here. I'm just copying this formula. Okay, so this is the formula that we need to follow. So what is tau BD? So tau BD for M20 grade is 1.2. Okay, so 1.2 times by 3.14 diameter 16 mm LD we need to calculate is equal to 5s. 5s is 0.87 Fy. Fy is 415 times 3.14 times 0.25 times 16 times 16. So using this, we can calculate development length and it will come out to be, just let me do the calculation. It will come out to be roughly one 1200 mm. So this is the development length that we need to provide. So how this is done? So I will just show you a rough diagram to just conclude this question. So suppose this is my column and this is my footing. We know the size and the depth of the footing. We know the cover. So my for one kind of for rebars will run like this along one direction and one will run along y direction. So these are my reinforcement from column. I need to provide two supplementary reinforcement here which are coming downwards, which will come till here. Okay, so this is my development rate, total development length, and it should be equal to 1200 mm. Okay, this total length from here to here, this is my development length. Okay, so this is how we need to provide development length and reinforcement along both the directions will run. So this will be 16 mm diameter at a spacing of 210 mm. Okay, and there will be some complementary tie reinforcement here. You need to provide at least two or three that we saw in the NPTEL discussion also. So like this you provide the reinforcement, tensile reinforcement in isolated footing. I hope everyone are clear with this question. Any doubts in the question? Yes, good evening. Okay, so this lecture is almost over now. You can refer to the recording. I will upload the recording on the YouTube channel, the link of which may be there in the Swayam portal. You can always check the Swayam portal. There is the link for the channel. So you can refer to that now. All the previous lecture and today's lecture, everything will be uploaded there. Okay. We have just concluded the final question. So if there are no doubt to anyone else, then I will conclude the session. So, in today's session, we started our discussion by uh, we started the discussion with discussion and then a numerical on design of slender column. Then we talked about RC footing, its role and how two different engineering areas are related to its design. Then we also talked about different types of footing. Then we understood different design parameter for design of a RC footing. This includes dimension, bearing capacity, thickness, reinforcement area, and development length. And finally, we solved a numerical on design of RC footing and saw design diagram for it. Okay, so this was all about for today's session. If you have any doubts, you can ask. Else, I will close the session.